Our next person who's going to be presenting is Colby Barth, who will be presenting energy efficient routing. Colby is a distinguished engineer at HPE Juniper Networking and has traveled from Philadelphia to join us today. It's Colby's first time presenting in Analog, and it's a pleasure to have him speaking with us today.
So my name's Colby Barth. Before I get started today, I just want to give some recognition to a few colleagues who also are contributing to this project here at HPE Juniper. My colleagues Ron Bonica and Tony Lee, without them, this project wouldn't be moving forward. I have a relatively simple agenda today. I'm going to quickly go through a little bit of a problem statement. I think it's important for everyone to at least understand the problem we're trying to solve and maybe what problems we're not trying to solve. And then I'm going to do a brief introduction into sort of like generic routing platforms. Again, it's a background that I think is important for understanding ultimately this routing solution that I'm going to propose to you today. And then I'll get into the meat of the presentation. So from a problem statement perspective, many of our networks today are designed for peak load, while also accommodating various kinds of failures. Different operators have different strategies for planning for these types of failures, but suffice to say, our networks are designed to absorb some load during one or more failures. While at the same time, our networks exhibit daily peaks and valleys in terms of this load. And in many networks, we see the valleys being 85% less than the peaks. This is what is illustrated in the picture to the right-hand side here. This is an actual graph of daily peaks and valleys from a real operational network. So our goal here is, during these non-peak times where we have a lot of idle capacity and thus wasted power, how do we temporarily redimension the network physically during these non-peak times and gracefully transition these unused or unneeded components into a power sleep state, and then of course transition them out of it without compromising the resiliency strategy for the network. So that's our sort of high-level problem statement. Now, of course, the devil's in the details. I do want to make one comment about some previous work that was presented here at NANOG. My colleague, Ron Bonica, presented a proposal for a power management portal. From a sort of 50,000-foot philosophical perspective, or from a problem statement perspective, the power management portal addressed the same problem in much of the same way. You'll hear me talk today about how we want to consolidate traffic so that we can thus turn off unused components. The power management portal essentially did the same thing, though it did it via a fully centralized controller that could consume enough network state to make decisions on consolidating traffic, say via a centralized PCE component, and then further decide what, when, and how to turn these components off. The proposal I'm going to present to you today, that I'm referring to as energy efficient routing, is a bit more of a traditional distributed routing protocols type of solution. I'm going to present a few extensions to our routing protocols and some modifications to our constrained shortest path first algorithm to do that traffic consolidation, and then allow our platforms to make independent decisions to gracefully power components on and off. So again, I want to acknowledge that there is some previous work here. The goal is the same. And before I get off this slide, I'd like to also note that these two solutions need not be mutually exclusive. There are ways to combine these types of solutions together that may fit your operational needs better than one versus the other. I'll touch upon that in the conclusion. So moving into a brief introduction of routing platforms. I'll move through this quickly. It's not the main topic of today's presentation, but again, like the problem statement, I think it's important background information. As you can see in the sort of diagram on the lower right-hand side, our packet forwarding engines and our optics consume the majority of the power in our systems. But to that end, right, the power consumption is very nonlinear. Right, it's affected by load on the system. The features that are implemented for each component within the system, which is depicted in the left-hand diagram. And even the same system at different ambient temperatures will consume different amounts of power, also depicted in the diagram to the right. To make things more complicated, we have various different kinds of systems, right? Here at HPE Juniper, we build modular chassis-based systems. We build fixed form factor systems. We make various cost optimization trade-offs for chassis across our product line. And if I throw other vendor systems into the mix, we have a very large matrix of differences in how our systems are built and how they consume power. So this is all to say that sort of the precise modeling of per component power and use by that per component power isn't really usable by our routing protocols. And because it varies in so many dimensions. As I mentioned in the previous slide about the nonlinearities, as well as the same systems operating at different temperatures, at different elevations, and different cost optimizations, all have different power consumption models and behaviors. These are attempting to depict two of these things in the diagrams at the bottom of the slide. You can see that the same system operating at Denver will consume more power than a system operating in Amsterdam due to the elevation differences. The picture on the right-hand side shows how the fans consume power as the ambient temperature goes up. So fans can make a large impact on how the systems consume power, which is independent of the types of features and the way we think about our routing systems from a routing protocol perspective. And then last but not least, there's a fairly strong relationship between the provisioned ports in a chassis and our ability to transition those associated components into a power sleep state. I refer to this as a dependency chain, and you may hear me talk about it throughout the rest of the presentation. In the lower right-hand picture, I'm depicting two dependency chains on the same line card. There's the gray chain and the green chain. And the easiest way to think about it, if you're not familiar with the terminology I'm using, is for a front facing interface or port to be active and up and forwarding traffic, obviously its PFE or forwarding engine also has to be active. And all of the associated connections between the interface optics, the PFE, and the fabric all must be active. So this dependency chain between a link that a routing protocol associates with and the physical dependency chain within the chassis is important. The other thing to note is that the actual utilization of our forwarding engines has a very small impact on power consumption. This is depicted in the left-hand diagram, where you can see that just the packet forwarding engines in this example, even forwarding no traffic at all consumes 635 watts. If I look at those same forwarding engines at 100% line rate, there's only an increase of 95 watts. So just moving traffic away from a PFE doesn't have a huge impact on the power consumption for those components. So that brings me to kind of getting into the details of what I'm going to propose to you today. I'm going to introduce a terminology called power groups. And the background of the sort of power group concept is as follows. Our traffic engineering networks often leverage various types of grouping techniques. For those of you who operate TE networks out there, you're probably familiar with admin groups or link affinities, and of course shared risk link groups. In Junos, we have some other mechanisms for grouping things together like abstract hops. But suffice to say, TE networks, it's a common thing to group things together and then use those groupings during path placement. What I'm going to introduce to you today is called a power group. A power group is meant to describe a hierarchical abstraction of the power consumed by a dependency chain, right? And these power groups provide a method of organizing interfaces by those dependency chain characteristics. And then our TE placement algorithm can optimize for power savings by distributing load across all of the power groups during peak times. And as we transition into the valleys during non-peak times, we begin to starve selected power groups and starve the selected power groups in a manner that may represent the most efficient use of the power groups or the cumulative least cost power across all of the power groups. So how do we do this? What does a power group look like? In the next section of the presentation, I'm going to talk about power group as a construct within our IGPs and specifically ISIS. I'm going to talk about an interface being a member of a group. We have the ability to advertise, or we'll introduce the ability to advertise a interface-specific power, a power sleeping capability, the notion of an IGP adjacency being asleep, and then the notion of bandwidth being asleep in the network. So power group, it's a top-level TLV that just describes the group, right? If you're familiar with the other types of groups that I mentioned, this is nothing different. But along with the group comes an identifier and a power associated with that group. And we have some embedded hierarchy. So the group can be a member of a parent. And this idea of having the identifier, a power value, and a parent ID is what allows us to describe at a very abstract way that dependency chain. In the picture to the right hand part of the slide, you can see I've depicted a blue, an orange, and a green power group. And the interfaces associated with each of those power groups are advertised as members. So the interface is advertised, or the link state is advertised as a member of the power group. If we dig into the example that I've depicted here a little bit, you can see that there is a local name. This is a construct in Junos we have for human readability. The group ID is what goes on the wire. Then, of course, the power value will also go on the wire. I'm not showing a parent identifier in this example. You can see that you have the ability to use various kinds of formats for the group ID. In this example, I'm showing that I've encoded a slot ID, a port group ID, and a forwarding engine ID and type into that power group. Remember this for later when I start to talk about how we actually do path placement. Interface power is relatively self-explanatory. Along with the power value for the group, we'll interface a interface-specific power. Again, this is something that will be used during path placement. Sleeping capability bit. This is an important construct for a topic that I'm not going to cover in detail today, unfortunately, due to time. It's worth a presentation by itself. But you can think of for a moment that we need to be able to understand that an interface is capable of being put to sleep so that we can decide how to use it during path placement, whether to have it be a point of consolidation or whether it be something we starve. The sleeping adjacency is also an important idea. Again, a concept I won't talk about too much today. I will discuss it a little bit at the end if we have time. But the sleeping adjacency is important because we need to remember that an adjacency has been put to sleep and differentiate it from an adjacency that has gone down. All right, so from or any platform guys out there that are listening, right? This is really just a new interface state to differentiate between up, down, and now sleeping. This is also an important concept for trying to proactively wake up a sleeping interface because we need to know that it has been put to sleep so that we can proactively wake it up if the need arises. Unidirectional sleeping bandwidth is a similar construct to the sleeping adjacency, where maybe a member of aggregated Ethernet bundle has been transitioned into a sleep state. We need to be able to advertise that a portion of the bandwidth of the aggregate Ethernet interface has been put to sleep. Again, so that we can we can remember and proactively wake it up, or potentially proactively wake it up. Okay, so for path placement perspective, before I get into some of the details of path placement, I do want to highlight that, or maybe reiterate, that I'm talking about a traffic engineering solution here today. While some of this information may be interesting to be flooded around the network, we're really talking about the ability to use traffic engineering techniques and TE placement techniques for placing demands on the network. In other words, our goal here is to minimize power consumption on the network by consolidating traffic so that we can transition unused components into this sleep state. So an optimization objective for TE path placement may be to use the fewest number of most efficient power groups for a given bandwidth demand. So the placing bandwidth is an important element of this solution that it isn't really new, but it's something important to recognize. It's kind of like a foundational sort of thing. The the value or the power value that is advertised along with the power group is used to derive a metric. And when we derive these metrics, we're going to take the values from the source interface and the destination interface and normalize them and use them symmetrically. The reason for this is that we want to normalize things so that if a very efficient or very low power group is connected to a neighbor's interface or neighbor's power group that is very inefficient or using a lot of power, we need to normalize the metrics. We're going to introduce two new mechanisms in our path placement algorithms. For to aid in the consolidation of traffic. I've talked so far about these power groups and their power values that we're going to use for metrics, so that we can find, say, the lowest cumulative metric across the fewest number of power groups. But for interfaces that are all part of the same power group, we still need a mechanism for trying to consolidate traffic. And you can think of these as kind of enhancements to our traditional tiebreakers. If you're not familiar with the term tiebreaker, it's sort of how we refer to how we choose a path or an interface to place a path on when we have multiple equal cost paths. The first thing we're going to use is a new low utilization bandwidth threshold. So we're going to ignore links with a utilization below a configurable threshold in hopes that this causes TE tunnels to be placed on links that are already being used. In other words, we want to try to avoid placing new demands on empty links. Try to always reuse links that are already being used. Now, if we can't find a path that respects this threshold for a given bandwidth demand, then of course we'll run CSPF again and select a new set of interfaces. The second item here that's equally as important is all of our path placement algorithms today are unidirectional. Right, ingress routers that are typically running CSPF, or even an off-box PCE is typically doing unidirectional path placement. And while there are like RSVP specific extensions for bidirectional LSPs, we are introducing something we call a symmetric most fill algorithm. And again, the idea here is to try to encourage symmetry without adding new protocol extensions or requiring the use of, say, off-box PC. And this encourages traffic in one direction to consolidate with traffic traveling in the opposite direction. In summary, we're introducing a way of grouping interfaces together by their power chain dependency. And we're introducing enhancements to our CSPF algorithm when we place demands on the network to encourage the consolidation of traffic within those power groups. We've done some simulations using real network topologies. I've depicted 3 of them here. They aren't massive networks, but they are large enough to, I think, provide a decent representation of sort of, you know, the scope of the problem that we're dealing with. You can see that there is significant savings to be had when we compare the network at its like fully operational state in terms of its power consumption versus using this power group and CSPF enhancements to consolidate traffic and turn off unused components, right? In the areas of 40+% to almost 70%. Now, I want to mention before I get off this slide 2, I think, important items. The first is that these simulations did not compromise resiliency. Now, the resiliency strategy that we use when we were doing the simulations is just single link failures. So the power save topology that's depicted on the bottom part of the slide is resilient for single link failures. The second thing that's important is the actual power values that I'm showing here. They assume that each packet forwarding engine used in the network uses 250 watts, and that there are 4 interfaces per packet forwarding engine. So we have sort of generalized how the platforms were deployed in these networks. And of course, very much generalized how much power they're consuming. So the important number on these slides is the percentage savings, and not necessarily the absolute power values. There is some good bedtime reading available if anyone's interested in digging into a little bit more details. We have a Yang model that describes the TE topology and database level attributes of the power groups. And we have a ISIS draft that describes the extensions I presented to you today. They are the sleeping neighbor and bandwidth, the capability, and then of course the power group definitions themselves. Now, what I presented today is really just like the routing side of things. So they are routing protocol extensions that can be used either by centralized PCEs or in distributed architectures, but they are just the routing protocol extensions. By themselves, they don't really do anything other than help consolidate traffic. I mentioned a few times in the presentation that there are other topics that I am not going to cover today. The first one I'm going to talk about is the first one I'm going to briefly mention is the second bullet point, which is I talked about sleeping bandwidth and sleeping adjacencies and the potential need to proactively wake up things. As you can imagine, it takes time to bring up a line card or bring up a forwarding engine or even bring up interfaces, varying from seconds to minutes depending on what has been turned off. If we need, we have mechanisms that we've also are in the process of prototyping and have already simulated on how we can estimate future demand and then proactively wake up sleeping components when needed. If you're familiar with how bandwidth estimation works in, say, MPLS auto bandwidth, it's not unlike solutions like that, where you can continuously compute the available bandwidth on a network or on a set of paths that may be available for a given TE tunnel. And if the computed available bandwidth falls below some threshold, you can begin to wake up sleeping interfaces. Graceful transitions between up and power sleep is also an important topic that I haven't covered today. That once we consolidate traffic, how do you actually turn something off, or how do you actually transition into this sort of sleep state? Again, we're looking at extensions to existing protocols like LACP or LLDP for exchanging power state information between adjacent peers, and then communicating the desire to transition something to sleep and or wake it up. And I mentioned in the very beginning when I highlighted Ron Bonica's previous presentation, this is an area where maybe a controller may fit the operational model better. Once the network has consolidated traffic, either in a distributed fashion or via centralized PCE, maybe some other application is going to come down and turn things on and off as needed. So again, I think the solution that I presented here today does not eliminate the use of controller applications in some parts of the solution where they make sense the most. The third point that I've mentioned a few times here about never compromising resiliency. I'm going to, I guess, maybe go on record since I think this is being recorded. It's dangerous to turn things off, and we recognize that. So how do we ensure that we don't bifurcate the network by unintentionally turning something off, even if there's no traffic on it? again, maybe at a future NANOG or another presentation, we can talk about how we also dynamically compute a resilient topology and not advertise that resilient topology as power save capable. And this would in turn prevent any types of bifurcation, and it could be aligned with, or will be aligned with, various types of resiliency schemes. And then last but not least, this solution sort of supports centralized and distributed architectures. In the traffic engineering group here at Juniper Networks, we're not religious about centralized versus distributed architectures, nor what TE transport protocol is being used. What I presented here today are IGP extensions that can be used by any TE placement protocols, be it RSVP or segment routing. It's worth highlighting that bandwidth management is an important component of the solution. So in the segment routing case, a centralized PCE or centralized resource manager is likely going to be needed. And then this is my last slide. We have a prototype underway. And if there is any interest in contribution, please reach out to myself or Ron Bonica or Tony Lee. And with that, I will close the presentation with, I guess, about 3.5 minutes for any questions.
It looks like we have one online question.
Correct. Well,
Okay.
One question from Navindu Senior. It looks like you have chosen to use a ISIS TLV, which appears to be limited to ISIS use case. How would you apply this to ECMP path?
Can you repeat the last part of the question? How would I apply this to?
How would you apply ISIS TLV to ECMP path?
To an ECMP path?
Yep.
Well, so the power group membership information will be flooded throughout the network. So within the traffic engineering database, whatever your path computing entity is, will have all of that available information. Now, what I proposed when I was talking about the path placement enhancements, the CSPF enhancements for consolidating traffic, we would essentially be, I guess, obviously using ECMP only if it's needed. And maybe a good example would be that, let's say you have a 16-way ECMP somewhere, and the load during your non-peak time is, say, 10% on all 16 paths. Now, there's no need for us to maintain all 16 paths when each one's only 10% loaded. So maybe we consolidate it to 4 of the 16, so that 4 links are running at, say, I don't know, 60% instead of 10%. And then the remaining 12 ECMP paths or ECMP links can be transitioned to power sleep. Does that answer your question?
Hopefully. Thank you.
Okay. Yep.
And we have one more in the room.
Hey, Colby. Steve Ulrich with Nextstop. I was curious, two questions. One, what's the class of traffic you anticipate being subjected to this additional selection criteria? I guess when I look at most folks applying traffic engineering, there's focus on other parameters which are driving link and path selection, and power is not the primary. Is this to be applied after things like bandwidth, path latency, or some other characteristic is to be evaluated?
Yeah, of course. I mean, we will honor any existing optimization objectives. Let's say you're doing, lowest cumulative delay, right? That optimization objective would still be used when we come up with the modified metric taking into account the power. Similarly, for things like, I don't know, avoiding black links or avoiding red links or, those types of admin group exclusions would, of course, always be honored. Right, so this is, an addition to the existing TE constraints and optimization objectives that we're already using.
Okay, thanks.
I would like to just add one more thing. As far as, if like class of traffic means to imply like quality of service, and like service steering and things of that nature, we're obviously kind of assuming that if the goal is to save power, then all of those classes of traffic are subject to this additional optimization objective. Now, maybe your EF traffic is also being routed by lowest cumulative delay. As I mentioned earlier, those would of course be honored first. So within the power savings strategy, we would find the lowest cumulative delay path.
Right on, thanks. And then I was curious about incorporation of like adjacent equipment power utilization. So like line systems or something along those lines, which would obviously have a impact on the overall power cost associated with a given link. Is there a mechanism, and apologies if this is covered in the draft, but for getting that hinted or encoding, say the a transponder's utilization or something along those lines, do you assume that those are statically configured properties of the link? Or is there a way to infer that from LLDP or something?
Great question. I guess I would answer it. The goal of the ISI extension, or the IGP extension, rather, is to be able to give you as an operator an abstract way of describing power, right? So, how you describe power and whether you include the line system in the dependency chain is something that we sort of leave up to you. You'll see, or you may not see, but what we're doing right now in our prototype is giving you the ability to actually configure these abstractions. And we have our own automation scheme for how you can associate router-specific power attributes to the dependency chain, but they need not be adhered to. So you can. That was a long-winded answer per se. The abstraction hopefully allows you to describe line systems and whatever you want within the chassis.
Cool, thanks.
All right, Colby, I think you're off the hook now.
All right, thank you.
Thank you so much for your presentation.